You know what? We've drawn a lot of molecules, we've drawn a lot of Lewis diagrams, you've probably even used some molecular models at some point to build little molecules, and you might have wondered, how do we know what they look like if we cannot see them? And the answer is going to come down to this. VSEPR theory, which stands for valence shell electron pair repulsion theory. It's pronounced VSEPR, and I'm going to call it VSEPR from here on out. Now, you might wonder, what does that even mean, valence shell, blah, 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 blah. Well, what it comes down to is working with charges, where we know like charges repel and opposite charges attract, but we're not really going to be dealing with too many opposite charges. It's going to come down to like charges. And bonds have electrons in them. Electrons have the same charge. So we're going to have electrons that are found in bonds. We're going to call those bonding pairs, BP for bonding pairs. We're going to have electrons that are not in bonds. They're just sitting on the central atom. We're going to call those lone pairs, non-bonding pairs, but I usually use lone pairs, or LP, and they're, as I said, not bonding. And they're going to repel things. And what happens is they're going to repel to the point where I've minimized the repulsion. Okay, so they're going to try and get as far away from each other as possible. Because they're within one molecule, they're pretty limited to how far away they can get, but they're going to do as far as they can go. And then that will determine the overall shape of the molecule. From there, we're going to talk about shapes, VSEPR shapes, based on this valence shell electron pair repulsion theory. All right, so let's get some background here. One of the things that's going to become important is the strength of the repulsions. Now for us, it's just going to be a qualitative thing. They're all going to be, well, we're going to lump a bunch of things together. So lone pair repulsions are going to be the strongest. So those absolutely have to get as far away from each other as possible. Bonding pair lone pair is also fairly strong, but not as strong as lone pair. So if I had to put two things together or closer together, then bonding pair lone pairs are going to go closer together than lone pairs. And then finally, bonding pairs, yes, they're going to repel each other, but if I had to throw a lone pair in there, those two bonding pairs, they don't mind being a little bit closer than the lone pair. Okay, so really what it comes down to. Now in some cases it's not going to matter because there won't be too many choices, but there are a few places where we do have a choice. Not really a choice, but do I put it here or do I put it there? Then we're going to need to look at that strength of repulsion list. Okay. Thinking also that an orbital is not a physical thing. I can draw it as a physical thing, but it really isn't a physical thing. It's just where we're likely to find the electron. And where I'm likely to find the electron is also going to be influenced by repulsive forces or repulsion forces on that electron. That's going to push that orbital, that's going to push that area of likely finding the electron somewhere else. And then multiple bonds, they are going to behave as if they are a single bonded group. We'll come back to that in more detail another time, but two single bonds behave differently than a single bond plus a double bond. So two bonds in both cases, one counts as two, the other counts as one. We'll get there. Okay. I think you should write this down. And it's a chart where I'm looking at number of bonding pairs, number of lone pairs, the class. I don't care about the class. It doesn't mean much to me, but some people do find it helpful. And then the shape. So right now, we're not talking about lone pairs. We're getting the basic shapes. So everything is going to be bonding pairs. Lone pairs we'll come back to another time. A class, I'll show you a few, then you can decide what to do with it. But the name of the shape and what it actually looks like is actually quite important for us. So what if I have two bonding pairs, no lone pairs? I can give it a name for that class, AX2, which just means A central atom, X bonding groups, two of those. If I were to draw that or build that and try to get those groups as far away from each other as possible, then they're going to be 180 degrees away from each other. Okay. What if you only had one? Well, at that point, there's not much sense talking about the thing because you've got one atom, another atom. Right. So the shape of the molecule only becomes relevant when you've got more than two or more bonded groups. Excuse me. So this is true for two single bonds or two double bonds, or a single bond and a triple bond or something like that. There's lots of options. If I have two bonded groups, no lone pairs, it's going to be this. Well, that's a straight line. Atom 1, atom 2, atom 3, straight line molecule, we're going to call that linear. They would have bonding angles of 180 degrees. By the way, the bonding angles themselves aren't going to be relevant or not going to be very relevant. I'm never going to ask you what's the bonding angle in this kind of thing, knowing the name. If you don't know the name, draw me the picture and then we can work with it. If I had 3 bonding pairs and no lone pairs, then class becomes that. Then it looks something like this, where I've got 1 central atom, 3 bonded groups. They're going to try and get as far away from each other as possible. They're going to repel each other to the point where they're nice and balanced and sort of roughly the same distance away from each other of 120 degrees. Again, the bond angle itself doesn't matter, but they would all be 120 degrees. There are things that are going to affect that, but we're not going to worry about it right now. We would call that trigonal planar. All those things lay in the same flat surface, or they would all lay flat on a surface. That would, the mathematical term for that is a plane, and the bond angles are 120 degrees. What if I went to 4? Well, 4, if I were to ask you to draw a Lewis diagram, you would end up drawing something kind of like a square or a cross, where central atom, then group, 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 where there would be top, bottom, left, right. But in reality, that molecule has 3 dimensions available to it. So if you were to work with the models, it would end up looking something like this, where it becomes almost a little bit more like a bird foot, where I've got 2 that are kind of, one going a little bit forward, one going a little bit back. Bond angles there are going to be 109.5 degrees all the way around. So I've only picked 1, but they're all going to be the same. If you were to make the bonded atoms the points of a 3-dimensional shape, you would call that shape a tetrahedron. We don't really care about that, but we do get our name for that as the tetrahedral. Okay? Bond angle is 109.5 degrees, a bunch of molecules that do that. 5 bonded groups with no lone pairs. This is one where when we eventually get to lone pairs, this one is one of the ones you want to put a little star beside because it matters. This one, there's no way for all the groups to be equally apart from each other. You have to end up with this somewhere combination between linear and the trigonal planar, where some of the bond angles are 90. So between the, if you think of those 3 as going through this surface, this flat spot here, and then one straight up and down. We'll give names to that. One's going to be axial, one is going to be equatorial, and then 120 through the triangle. I've drawn a Lewis diagram of something here. We'll talk about the dashes and wedges another time, because that's sort of a notation we can use to represent 3 dimensions. Thing coming out toward you, or the dashes going back away from you. Okay. The name for that is trigonal bipyramidal. I've heard slightly different pronunciations, trigonal bipyramidal, but what you're going to hear me say is trigonal bipyramidal. Bond angles are 90 degrees, as I mentioned, and 120 degrees, depending on what you're looking at. 6 and no lone pairs. Looks like that. Now this one, no matter how you rotate that thing, it's going to look the same. You're going to have 4 going around the equator and 2 forming an axis. So you get a nice symmetry there. Lewis diagrams, you can't really draw that because it's hard to draw in 3 dimensions on a 2-dimensional piece of paper. Again, if you were to put the corners, or put those bonded atoms into the corners of a mathematical shape, oops, I'm a little bit behind myself here, 90 degrees all the way around. If you were to put the bonded atoms into corners, that would be an octahedron, an 8-sided thing. So we call it an octahedral. And the reason I mention that is because we have 6 bonded groups, but we call it an octahedral. It's just the name of the shape that you would make from that. Things we need to come back to later. Well, what happens if you have lone pairs? That's a totally another thing. Let's get comfortable with the basic shapes to start. What do you do with double and triple bonds? Like, I know I said that we treat them as a single group, but why? What's going on with them that is so different? And the other thing is, how does it happen? Like, we were talking about orbitals, and I just kind of went into these shapes and hinted at orbitals, but what's actually happening that I can get these things to be equally apart from each other in many of the cases? Like, think about what we know about orbitals. Okay, that's going to have to change. But at this point, what we know is the names and shapes, and we should be able to draw them like on a 2-dimensional page, something that represents 3 dimensions. Okay, and as I mentioned before, if you really struggle with the names but you know what it looks like, I can work with that too. Anyway, we'll talk to you another time.